Welcome to this next class on fundamentals of acoustics. In the last class we looked at the mathematics and the physics of the on axis pressure radiated by a piston in a baffle. Today we said we will look at the off axis behavior. And we have derived the expression already. So the P at a certain location R from the center of the piston at a theta angle is given by J omega rho is let me write it in terms of source strength J omega rho Q e to the power of minus j k r by pi r j1 k a sin theta by k a sin theta. Okay. Now as k a sin theta approaches 0, this expression approaches the value of half. Okay. So let us say Ka goes to a very small value. Okay. Ka has gone to a very small value, or again monopole approximation less than 1, much less than 1. Okay. Then what we get is P r comma theta is equal to j omega rho q e to the power minus j k r by twice pi r. Now if you remember, del square plus k square g being minus delta of r minus r dash. Okay. The green free space green function was e to the power minus j k r by 4 pi r. So it does not have pressure units. Okay. It has 1 over length units, but if we add j omega rho q, okay, then this becomes pressure. Okay. Now this is a pressure due to a very small source, pressure from a monopole. Okay. Now we have here the expression for a monopole on a baffle. Monopole on a baffle. So there is only a difference of 2 here. So this is twice the value of this. So what essentially happens is that you have a baffle and you have a source piston, let us say, of this dimension. Now slowly the Ka is reduced so that my piston starts to become smaller and smaller and smaller. Now we have a monopole approximation that is sitting on a baffle. So the direct pressure comes forward. However, the pressure that is going backward gets radiated, and because the source is small and sitting on the baffle, it comes back in phase, and so instead of this single monopole pressure, I get twice the pressure. So I get twice the pressure when I put it on a wall. That is this expression in the monopole limit. Okay. So that is one part of it. Okay. Now for the normal expression we have J1 of Ka sin theta by Ka sin theta, and theta goes, this is the piston, theta takes values from 0 to pi by 2, okay, from 0 to pi by 2. This is the 0 position, theta equal to 0, okay, theta equal to 0. This is my piston, this is the axis of symmetry, okay. So theta takes values from 0 to pi by 2. Okay. Now, so that means at 0 sin theta is 0, okay, at theta equal to 0 sin theta is 0, and at theta equal to pi by 2 sin theta is 1. So this expression goes from 0 to 1 only once, because there are no angles bigger than pi by 2, and now this value is Ka. So the maximum value of Ka sin theta is Ka. Okay. So now if we plot the magnitude J1 of Ka sin theta by Ka sin theta, okay, or we just plot J1 of Ka sin theta by Ka sin theta, then it looks like this. It starts off at a half, and then it has this oscillatory behavior, and it starts to decay away. Okay. So this is Ka sin theta. Okay. Now if Ka is very small, okay, then Ka sin theta can go from 0 to Ka, which is a small value. This is Ka, that is it, okay, because Ka is very small. Okay. So now if we look at this expression, so if we plot this physically, okay, at small values of theta we have a peak, and by the time we reach theta equal to pi by 2, we have slightly dropped. We have only slightly dropped. So the plot looks like this. it's pretty much non-directional. This is the pressure picture. For Ka much less than 1. Okay, so this function which is sitting over here, it changes only this much from theta equal to 0 to theta equal to pi by 2. Okay, but suppose I increment Ka a little bit, okay, so that the Ka value can reach till here, suppose. Okay, then what happens? So here I have 0 and here Ka sin theta has become Ka. That means theta is pi by 2 at this place. Then what happens? As I move from theta equal to 0 to theta equal to pi by 2, I pass through one dip, I pass through one 0. So I start over here. So once I choose a Ka in the expression Ka sin theta, Ka becomes a constant. Only theta changes. Okay, please understand it that way. So once Ka is taken a middle value, then Ka is fixed, and then I have Ka sin theta. So Ka sin theta starts at 0 and approaches the value of Ka at this location. This is where theta goes to pi by 2. Okay, so now what happens? I start off here, and I go through a 0. Okay, and if I take this absolute of this, because the negative will change once phase comes in, e to the power j omega t oscillation comes in, this will go negative and this will go positive. So that's unimportant. The peak is what is important. So again a little bit beyond I get another peak. And beyond, of course, I go down. Okay, a similar thing, symmetric thing happens on the other side also. If I take a very large K value, let's say hypothetically some 100 or something, and Ka sin theta is 100 sin theta. Now theta varies from 0 to pi by 2. So somewhere here theta becomes pi by 2, so that the value of 100 is reached over here. Then as I move along theta, I get a very narrow peak. Now I will get a very narrow peak. Okay, because Ka is very large, theta will move very quickly and I will get the first dip very quickly. Let me plot it with blue. This peak becomes narrow, and then very quickly, because Ka is large, another peak will come next to it and will also disappear, and then another peak will come next to it and a 0 node in between. So every time you get a peak, you get a 0, then you get another peak, you get a 0, then you get another peak. So in this manner you will get these side lobes, and the number of side lobes have gone up because my Ka has gone up. Okay, For a smaller value of theta, I get the same earlier value of K sine theta, and therefore the lobes become narrower. Okay, and the next peak comes more quickly, the next zero comes more quickly, the next peak again. So now you have this lobe type pattern that has increased. Okay. Now, why does this behavior happen? Why this behavior happens? Okay, we have discussed what happens on axis. Okay, so now we are discussing why it happens in the theta direction, why this lobe pattern happens in the theta direction. Okay, so now let's see why that happens. So again we have a baffle and my piston is here, and then the baffle again over here. This is the piston axis or z axis. Okay, and we are looking at an off axis point over here. Okay, and let me join these lines here. Let me join these lines. Okay, so let us say this angle is theta. Then the remaining angle is 90 minus theta. Okay, and this whole distance now is twice a, the diameter of the piston. Okay, now again the piston is oscillating back and forth with Vn e to the power of j omega t. Okay. Now what happens is that again a pulse is sent from here and a pulse moves from here. Okay, simultaneously. That means what? That means as time goes by, this peak is moving at the speed of sound, and at a certain time the peak will hit the point, observer point off axis. This is the observer. Similarly, from here, when this was released, at the same instant a pulse is sent from here. Okay, now he is traveling at the speed of sound and he reaches here, that peak reaches here. But what happens is that because of the path difference, they don't arrive at the same point, same time instant. This point has this path to cover, whereas this pulse has this path to cover, and this is the path difference. Okay, so if this is theta and this is 90 minus theta, in the far field, we are in a far field, this is also approximately 90 minus theta. Okay, so this distance is cos 90 minus theta, which is sin theta into 2a. So this distance is 2a sin theta. Okay. This is the path difference d. Now for a path difference d, the phase difference is k times d, where k is either omega by c times d or twice pi by lambda times d. Okay. So now if this kd is significant, okay, that means d is a significant part of lambda. This d is a significant part of lambda. D by lambda is not a small quantity. Okay, phase difference is not a small quantity. Then what happens? Twice pi d by lambda can approach pi, give or take. Okay. So if that happens, what happens to kd? Kd is approximately pi. Okay, that means the phase difference over here is 180 degrees. When the peak from here arrives, the trough from here arrives. Okay, so that's what is happening. Then you can have destructive interference. You can have destructive interference. Or cancellation. Okay. And so either when A goes up, then twice A sin theta is equal to D can go up. Okay, or when kd goes up, that means omega by c into d goes up, which means omega goes up. Okay, so either when the piston dimension is big, piston radius is big, or frequency is high, or both. There will be locations, there will be angles where kd can acquire the value of pi. Okay, actual situation is more complicated because it's a full continuous piston moving back and forth, and it's not just radiating from one end and the other. Everywhere there are wavelets coming out, and how they will interact and create zeros is more complicated. But this is a small schematic thought process that tells you how constructive or destructive interferences can occur. And so because of that, okay, because of symmetry, on the axis you will always have a peak, and slowly away from the main axis you will get a dip 0, and then another peak and a dip, and another peak and a dip, and so forth. and this depends on Ka of the system, of the piston system. That means depends on the radius, it depends on the frequency. Okay. I hope it's clear why these interference patterns occur. And if you look at this from a front, okay, from the front, if you look at it, this is the central dome, central lobe, okay, it will fade away, and then this will be the next peak line. This is of course, okay, let this be the peak line, then this fades off into 0, then you have the next peak. So it looks like a flower if you look at it end down. Okay, and of course you pick any direction and move forward, it has a 1 over r decay. Okay, you pick any direction and move in that direction, it has a 1 over r decay. If you move in the axis direction, it has a 1, after the peaky behavior is over, it has a 1 over r decay. Okay, so that's how the piston in a baffle behaves. Piston in a baffle. Okay, so with this I close the piston in a baffle derivation and the physical explanation of how it behaves. Okay, in the next class we will see the behavior of the piston on a sphere, piston on a rigid sphere, and its subtopics like point source on a rigid sphere, etc. We will see the physics of that in the next class. Okay, I will close the lecture here. Thank you.